Before I start, like all academics, especially those that have been around for longer, I don't actually do any work myself, so I want to acknowledge the people who've done the work, and that is my PhD students, past and present. Paras, who's sitting here, is the current PhD student, and Ignacio, Pascal, and Simon, who are past PhD students, and Pascal is also here today. And wherever possible, I try and name check them so you see their work, and I will come back to that later. So, what am I going to talk about today? Well, I will talk about unsteady flow, because when I was asked to give a lecture, I thought unsteady flow is the one topic where I have lots of nice videos, and it's something that it relates to daily life, and I can get quite excited about. But I then really struggled to think what precisely about unsteady flow I would talk about. What is the hook? What is the story that I want to tell? And it then happens that I had a conversation with my dad about something totally different. And I should say my father is not a scientist or an academic. And he had read something, and he made this sort of flippant remark that in 100 years' time, anything anybody does is all forgotten. And I was saying to him, well, hang on, that's a bit weird, because the work we're doing right now is we're frantically trying to read and understand papers that were written 100 years ago, working with theories that were developed 100 years ago. So I'm going to take that as my topic. I want to try and plea for some of these very old-fashioned things to show that they are still valuable and important today. And I don't know if we have any third-year engineering students here, but they all have to study something called potential flow. And they may be sitting there thinking, this sounds really, really old-fashioned. What is the use of it today? And what I'm hoping to do is, through this lecture, is first of all, tell you that sometimes analytical or theoretical work can be actually really interesting if you relate it to something. And there will be lots of experiments that I'll show you. Not that I will do, but that I will show you. But also that this old stuff can still have really good use today. So that's my aim for today. So I'll talk about potential flow. I've already mentioned it. I will explain what that is and how it introduces us to some interesting ideas or helps us to think about things in a certain way, particularly something called added mass force, vortices and forces. So this is really the topic of the lecture. And then I will try and demonstrate that these old ideas still do have value today. And in particular, I will talk about gust encounters, but I'll also mention something else, which you shall see. So, what is an unsteady flow? An unsteady flow is a flow of a fluid, so that's a gas or a liquid, that changes with time. That's what we mean by unsteady. So if you look at one moment, it looks one way, and you look a split second later, it looks totally different. That would be a good example of an unsteady flow. And there is one example that we are all very, very familiar with. Okay, that's slightly dark, but that's a hummingbird, so flapping wing flight. Apart from the really big birds that glide very lazily and look more like gliders, all the smaller birds keep themselves aloft by making use of unsteady flow. They're constantly, if you think of a wing flapping, that always sees a different flow. From 1 second or split second to the next, the flow field looks totally different. That's a really good example of unsteady flow. Another more technical example is this vertical axis wind turbine, where one of these blades, they keep rotating around their axis, and here's a simulation of that. As they go around, they constantly see a different flow. The wind comes always from a different direction. They might be diving through the wake of one of the previous blades. So that's a very technical example of a typical unsteady flow. The one that has inspired us is trying to fly little vehicles like drones or smaller vehicles in an environment where the airflow is very, very gusty. So typically in cities, you don't have a steady wind. You have lots of gusts, and you can have things like around a building, you can have a sudden updraft. And if you fly in there, you are experiencing gusts, and here's somebody trying to fly a drone in exactly that environment. And even though these drones are controlled, it's not quite as easy as it looks. So that is, in a nutshell, an introduction to unsteady flow. The thing that can happen is that they can all produce very large and, of course, unsteady forces, so forces that peak and trough and so on. And what we want to do is understand the main mechanism by which these forces are produced. What are the key things? So we're more after a sort of low-order understanding. We don't want to calculate the forces to 0.01%, but we want to understand what is it that causes them. Because if we get that understanding, then we can use that to maybe control such flows or predict flows better or maybe design things better. So that's kind of the rough area that I want to talk about today. Now, for those of you that are very pedantic and scientific, I have to say right from the word go that everything I'm showing you today and the way I will talk about everything is purely two-dimensional. Now that, don't all rush out. I know the real world is 3D. I know a bird is three-dimensional. But you'd be surprised how far you get even with a two-dimensional understanding. Even the wing of a bird is relatively uniform, so I'm basically looking at the slice across the wing. So I know that's a limitation, but bear with me. Okay, now, the theory that I'm talking about, it is even older than 100 years. It's incompressible potential flow. And why do we have theories? Because before computers, people had to somehow find solutions, find a way to predict or understand these flows, and they had to do it with pen and paper. They had to sit down and derive analytical solutions. Now, the only way you can do that is if you make the problem simpler. If you really try to solve the full equations for fluid mechanics and Navier-Stokes equations, you need very powerful computers, and in fact, even today's computers are not powerful enough to do it properly. So they had to make simplifications, and the two major ones are that they neglected compressibility and they neglected friction. So what does that mean? Compressibility is that air is quite compressible, for example. So if you take a bicycle pump, put your finger on it, and you squeeze it, you can tell that it's very easy for you to change the density of air. That's basically compressibility. Now, limiting ourselves to treat the density constant to say, no, that doesn't happen, sounds very crude, but actually it isn't. Because, first of all, a flow in water, for example, is very similar to one in air, and the water density hardly changes. And secondly, it turns out that in most practical airflows, the density changes very little. You have to go to supersonic flow before you have to really worry about compressibility. So the compressibility assumption is not such a big deal. It's actually quite all right. We're fine with that. The friction is a little bit more problematic, and I will come back to that. But for now, they assumed that there is no friction. And then what did these people achieve? Well, they were able to derive analytical solutions for a lot of practical flows. So here is a flow around a circular cylinder. So imagine stream flow from left to right. Here's one around a vertical flat plate. And here's one around an airfoil. And some of these, they look quite reasonable, quite good for something you can do with pen and paper, or that our third-year engineering students can do. But we have neglected friction. And I've already said that that's causing us one or two little headaches. And the first is that the flows don't really look quite like these flow fields that I've shown you. What do I mean by that? Well, look at this circular cylinder. This is what it looks like in potential flow. And in real, here's a picture from my lab. There's a circular cylinder. And what you see on the front, it looks similar. But then on the back, the flow doesn't want to follow it. What actually happens here is what we call separation. The flow stops following the contour, the surface, and it moves away, and we get this wake region. And that is a separated flow. And in order to get separation, you need to have friction. And if you neglect friction, you won't get separation. This is even more obvious in this case here, because even here, you can all probably guess that the flow isn't going to do that. It's going to do something like this. And here you have a massive big separated region. So that is a real drawback for potential flow. And you might say, I Googled it this morning for some reason, and I found out that Richard Feynman, who I admire a lot, he said potential flow is only really good for dry water. So I disagree with him, because we can sometimes, the airfoil flow, for example, is actually not that bad. So even neglecting friction, we do sometimes get useful results. Now, I should warn you that, however, even on an airfoil, the absence of friction causes us problems, because sometimes the flow looks like this. And now you see we have separation here. The flow stops following it. So we'll have to keep that in mind. The other downside with neglecting friction is that we can't calculate drag, at least not in steady flow. And that is quite a big limitation, because often drag is the one thing we really want to know. So should we go like Feynman and say this is all garbage, let's not bother with it? Well, I'm pleading today that no, we shouldn't, because it does help us to understand complex flows. As long as we know what its limitations, we can get some really good insight out of this. And that's what I'm out to demonstrate to you now. And the first example for that is the added mass force. So added mass force, if you do the typical research that an undergraduate would do, which means you type it into Google, you'll get the Wikipedia definition for it. And it says it's the inertia added to a system because an accelerating, decelerating body must move or deflect some volume of surrounding fluid as it moves through it. Now, what does that mean? It means that if you have an object like this in still air, which this room pretty much is, if I want to suddenly accelerate it, so I'm in still air and I suddenly want to move it that way, the air in front of it has to get out of the way. The air behind has to rush in to fill that void. So what happens is I'm not just accelerating that object, I'm also accelerating some fluid particles all around it. And that means that the force I need to move this object is not just to overcome the inertia or the mass of that, I also need to move a little bit of the surrounding fluid. And that means this will feel heavier than it really is, and that amount by which it feels heavier, that's what we call the added mass, and that is the added mass force. So that's the hand-wavy explanation, but because this talk today had the name lecture in it, I feel that I also have to give a little bit of a lecture, so I'm going to apologize right now. There's just a tiny little bit of math coming. If you don't like math, don't worry. I will give you some ideas of how you can do stuff in your bathtub in a minute. But first, the math. We go all the way back to Newton. Newton's second law says force is the rate of change of momentum. And if you want to apply that to a fluid, it looks like this. Now, that equation, what does that actually mean? Remember, I'm doing this in 2 dimensions. If you look here, that integral, and it's an area integral of density times a velocity vector over the whole area. That basically is simply going in your flow field and picking every little bit of area element, looking how fast this is moving or what is its momentum, and adding it all up. So that integral is your total fluid momentum. And the force must therefore be the time derivative of that, if that changes. So that in itself is not super instructive. How does that help us to understand added mass? For that, I'm now going to ask you to indulge me and do a thought experiment. I want you to imagine a flow field, and this sounds very abstract, that is self-similar but unsteady. So what the heck does that mean? Self-similar, what I mean is imagine a flow field that always looks the same, but is not a steady flow. Now, from everything I've said right now, that sounds a little bit odd, but here's an example. Potential flow. This cylinder, the potential flow solution for the flow around that cylinder, I've already showed you, it looks like this. Now, it's perfectly possible that the incoming velocity here might change with time. So it gets faster and slower. And while it does that, the streamlines don't change at all. So that's what I mean. This is a self-similar flow field, but it does change with time because the velocity changes with time. It gets bigger and smaller. And I hope you can just follow me that far. And if that's the case, then a velocity at a random point, so this is just a random point here, will now change with time. And of course, the velocity also depends on where we are in our flow field. But now, because it's self-similar, we can make use of that. So for example, that velocity, if I double the incoming velocity, I would expect that velocity to also double. If I half it, I expect it to half. So I can write the velocity at any point in this flow field simply as the product of the incoming free stream velocity times some kind of proportionality. So, for example, at that point here, this is a stagnation point, there the velocity is always 0, so my k at that point would be 0. At that point on the shoulder, I happen to know, because I know this potential flow solution really well, here the velocity is always exactly twice the incoming one, so there my k would be 2. Anywhere else it would be somewhere in between. And if you can have followed me that far, then the rest is relatively straightforward. We can now go back to the equation, and we rewrite this. We put that equation into here, and that allows us to separate this out. And we're left with an integral here, which is not dependent on time. This is just an integral of this proportionality constant. And the time derivative is now simply the global acceleration. How much does the overall u change? So you have a term that's not time dependent, and you have a global acceleration. And now suddenly, this looks just like F equals ma, mass times acceleration. So this looks like an inertial force. And in fact, this thing in 2 dimensions has the unit of mass per the 3rd dimension. If you did this in 3D, this would basically be the unit of mass. So that term in here, that is your added mass. That is how much fluid do you have to move with, your, when you're accelerating something. Sorry, got slightly. So what does that look like? At the moment, it's an integral, not terribly helpful. So let's take a real practical example, that vertical flat plate. Here, I know the potential flow solution. You don't need to know that, but you can now do and calculate that with pen and paper. And you find that that first term ends up being this. I've introduced a factor c. C is the width of that plate, or the chord length, hence the letter C. And if you now look at that, what that actually means, well, that's exactly the amount of mass that is in that circle of fluid. So what's happened is that with potential flow, I'm now calculating that if I take a flat plate, and I happen to have one here, and I want to suddenly accelerate it, then I need to move an amount of fluid that is as big as the fluid in that red circle. And that is an extra force on top of any drag force. And so here is what you can do in your bathtub. You take a kitchen spatula or something, and you move it first at a constant speed, just so you get a sense for what the typical drag is. So that's what I'm doing here. I'm moving it at a constant speed, and you can sort of see how much it's bending. That gives you a measure of the drag. And yeah, you can definitely feel it. There is a drag, but it's not all that much. But if you now want to accelerate it, and particularly if you want to accelerate it all the time, what I can do is do a sort of sinusoidal thing. And as soon as you do that, and I'm not even going all that fast, but I'm feeling a much greater force. And how much greater is it? Well, this is what that is there for. If you look at the size of this is roughly the diameter of the yogurt pot. So it's basically that amount of water that I'm constantly having to accelerate when I push this through. And now you can probably get a sense, even if you didn't see it, even if it wasn't a very convincing experiment, but I hope that gives you an idea of how big this added mass force is. Right. And that was pretty much all the math out of the way. So now let's do this experiment properly. And that was done by Simon, who's not here, the first PhD student in the list. Here in this picture, there is a flat plate. You just can't see it very well because of the illumination. And what we're going to do is we will accelerate it. It's at rest right now, and then we will suddenly accelerate it to the right. And we're also looking at the flow because it's very pretty. So here it goes. It doesn't look like the potential flow we've seen earlier because this is real flow with friction. But let's now look at the force measurement. Here it is. And what I want you to look at is that early on, when we first start accelerating this, we don't start at 0 with the force. We immediately kick in with this force here. And if you go into the equation for the added mass force and calculate it, that's how big it is. So, interestingly enough, for the very first split second of the motion, that equation, which you can derive relatively simply, actually gets the force that we're measuring absolutely right. Well, that's interesting, even though we have so many simplifications and we've neglected friction. Well, actually, if you go into this flow field and you look what it looks like in the very first split second, and with modern flow diagnostics we can do it, it looks like this. For the first split second, and this is a real measurement here, the flow looks remarkably close to the potential flow prediction. And in fact, it pretty much is. So before friction kicks in, before anything kicks in, you do indeed get that potential flow, if only for a split second. And here is another example. I have a circular cylinder in here. I'm accelerating that. That's a very pretty video. It's a little bit feeble, but I hope you do get to see it. And again, if we look at the force, so I'm sorry, this is a little bit messy. Pascal provided this. Not Pascal's fault that it's messy, sorry. I stole that picture and he didn't have an opportunity to make a nicer one. Just look at the black line here. That is the force that is being measured as we accelerate that circular cylinder. And this is the magnitude of the added mass force. And again, you see now for quite a bit, for the first half a diameter of motion, we pretty much get the force spot on. Yes, not 100%, I know, we're 10% out, doesn't matter. And if you look at the flow field early on, there it is. It looks exactly like the potential flow. So, what have we learned about this added mass force, which comes from potential flow? That it's an unsteady flow, force that results from object acceleration. We can totally predict it with an inviscid theory, which is quite remarkable. It's relatively easy to calculate. And it does get it right, at least for that first split second when we're from rest and we're accelerating. And if you look at the math, I've just told you how much water it is you're moving with that plate. You can imagine that if the acceleration is large, you can create pretty large forces. And I think that all of you are doing that without knowing it, at least those of you that can swim. So next time you're swimming, do a breaststroke and observe yourself. What are you doing with your hands? If you were just after steady drag, you'd get your hand moving as quickly as possible and move it at a constant speed to make use of that drag. But that is not what you're doing. You're starting slowly, and then you keep accelerating all the time. You're making your hand go faster and faster and faster because you're trying, without knowing it, you're trying to make use of that unsteady extra force you're getting when you're accelerating, that added mass force. So next time you go swimming, try it out and you'll see that it's right. Right. Another thing of potential flow that is often used are vortices. And we like vortices because there is a very simple solution in potential flow for a vortex. So a vortex is any flow field where all the streamlines are basically concentric circles, so that you're just going around in circles. And the potential flow solution says that the velocity tails off, so the further away you get from the vortex, the less this velocity that is tangential, and it goes exactly with 1 over r. So that's like if this is a hurricane, you want to be far away because then you have less wind, and the closer you get to the center, the worse it gets. Apart from the very middle where friction matters, but of course, potential flow doesn't do friction. Now, why do we like vortices? One, it's a very simple solution, but also because we can use vortices to build a complex flow field. So by adding a few vortices, at least on pen and paper, to our flow field, we can make something that looks quite interesting. And the simplest example is if you take uniform flow and you add a vortex, and you put the two together, you get something that looks like this. This is actually a pretty bad drawing, and I ran out of time to do something better. Now, you may look at this flow field and say, well, hang on, that looks a little bit bizarre. What is the use of that? Well, actually, surprisingly, that flow is a very good model of a wing creating lift. And here are the streamlines for a wing creating lift. And you can just about see some similarities to this flow field there. So in potential flow, if we want to model a lifting wing, what we actually do is we stick an invisible vortex in the middle of that wing, and we superimpose it to uniform flow. So vortices are great, but there are some rules about vortices, and one of those is from Lord Kelvin, who says they can't come from everywhere. More precisely, he said that the vortex strength in a flow has to remain constant. So we call vortex strength circulation. So if I say circulation, I apologize, I kind of mean how strong the vortices are, but it's becoming sort of second nature for me. So that means a vortex can't just suddenly appear from nowhere. Now, how does that sounds a little bit odd, so I'm going to try and demonstrate this to you. This is a tank filled with water, and these white things are particles to just show us what the flow is doing. Over here, I have an airfoil, or a wing. That black region is just a shadow. This is not in the flow. This is difficult to pull off. This is Paras's experiment, by the way, and his video. So ignore that, but here's a wing, and right now that wing is at 0 angle of attack, and it's a symmetric airfoil. It does not produce any lift. And then we will move that and then suddenly pitch it to create lift. So watch what happens. And this goes several times. And what you see here is clearly a vortex. So it becomes not very impressive if I stop it because we can't see it. But there is a vortex here that wasn't there before. So if Kelvin says vortices can't come from nowhere, if the total circulation has to be constant, there clearly is circulation here right now. The only way that can work is if there is the equal opposite circulation somewhere else that cancels it out, so the total remains 0. And yes, there is, because there's this airfoil here that's creating lift, and I just told you that in potential flow, we model that with a vortex. So what we actually have is we have that thing, which is called the starting vortex, and then we have this, which is, now we call it the bound vortex, is our imaginary vortex in the airfoil, which is the exact opposite of that. So in practice, this is just one demonstration that vortices in general tend to come in pairs. So you don't get a single one. As soon as you do something to the flow, you get a vortex pair. And in fact, that is one way for us to understand forces. Because, and that's the next thing I want to explain, whenever you put a force into a flow field, by some force or way or other, you generate two counter-rotating vortices. And we can do this, and this is something you can do yourself. So again, I'm going back to my trusted flat plate. If you suddenly accelerate that, you're clearly applying a force. So I will try and do that now. And in order to show you, I'm going to use the visualizer. And this is, again, something you can do yourself. Thank you. Now, okay, you want to see the flow. So very scientifically, I've got a tea bag here. So again, I'm trying to give you ideas of what you can do yourself. Okay, could have been slightly better, but we'll see. And then you can use this, or here's my kitchen spatula. Right, let me see if I can. This is, of course, highly risky, because if this goes wrong, I'll be really embarrassed. So here we go. And now I start. And it was probably not quite as convincing as I would have liked it, but let's see. When I tried this at home, tea was floating a little bit better. Let's do this. I'll do it in the other direction. And with a little bit of luck, I couldn't see what you were seeing. With a little bit of luck, you saw that when you move this thing, that there were two vortices coming off at the back. We can go back to here. And so what I did was I moved this out of the way, and I generated this pair of vortices. And you can even do this with a spoon in your coffee cup. Next time you drink a cup of tea or coffee, you can see that, and you can see those two vortices. And what we're interested in is forces. That's what this lecture is about. So the big question is, how big is that force? And in order to do that, we're interested really in the momentum in the flow, because we're already, we want to go back to Newton, force's rate of change. And here we're coming back to my dad, and who said 100 years is too long ago for anything to matter. Well, Lamb, he published it in 1932. I'm sure it took him 8 years to figure this out, so that was probably done 100 years ago. He calculated the momentum of the flow in a vortex pair. And this is what it is, J. And it's the density of the fluid times this gamma, and this gamma is the circulation. This gamma is the strength of one of these vortices. And remember, they're both of the same strength, just of opposite sign, so that's why there's only a gamma here. So one is gamma and the other is minus gamma. And d is the distance that they are apart. So that is the momentum of a vortex pair. That is an incredibly useful equation. So I'm going to put it up here, because if we're interested in the force, all we need to do is take the time derivative, and we are treating density as constant because it's incompressible flow. So we end up with two terms. There's two contributions to force. The first is if the gamma changes. So if you have two vortices in the flow field and they get stronger or weaker, or if a vortex appears out of nowhere, that's a change, clearly a change in vortex strength, then there must be a force involved. And the other term is this one, which is when that distance between them changes. So if the two vortices move apart or closer together, then again, there must be a force involved somewhere. And the interesting thing is that that immediately also explains lift, at least in a sort of abstract way, because if I go back to my picture from before, in potential flow, we have this starting vortex, which stays behind wherever we began creating our lift, and we have the bound vortex, which is tied to the wing, and the distance between the two changes with time, because this is flying at some speed. So even though these vortices stay of a constant strength, that second term now is rho gamma, and d dot is in fact the flight velocity. Anybody who knows anything about aviation knows lift is rho u gamma is a very, very famous equation. And there it pops right out. So to summarize what I wanted to say about vortices is they come typically in pairs. Sometimes, of course, you have lots and lots of little vortices. It's very difficult to see the pairs. But conceptually, we can just imagine that we have hundreds and hundreds of equal opposite vortex pairs. And whenever they change strength or move relative to each other, so whenever a vortex moves relative to its mirror, I call it, then there must be a force. And that is what we use in potential flow now to solve these problems. So this is now where I finally come to these equations that were derived 100 years ago. But in order to do that, you have to indulge me with one more little step, and that is instead of using individual vortices, we're using something called vortex sheets. And they are these whole thin layers of lots and lots of infinitely weak vortices all lined up in a row. And that is just very useful because what we can do is we can distribute them along the surface of an object. What do I mean by that? Let's go back to our trusted circular cylinder. This is what Pascal, who's here, did his whole PhD on. He effectively modeled the vortex sheet. He plonked a vortex sheet of unknown strength all the way around. And then what you do is you allow that vortex sheet strength to vary depending on where you are, as long as the total sum is still zero, because we didn't have any vorticity to begin with. And by doing that, you can do that in potential flow, and you can solve the equation, and you can calculate what that vortex sheet strength should be in order to get the correct flow field. And for a circular cylinder, it looks like that. So it looks like a sine wave. It's shown here as a function of that angle, so that depends where we are on the surface. And now that all seems very abstract, but it's actually turned out to be incredibly useful. And the reason why this is useful is because mathematically, the local strength of the vortex sheet is simply the difference in velocity between the two sides. It's very, very simple. And in an object like this, where we're wrapping the vortex sheet around the solid object, the velocity on the inside is always zero, because there's nothing moving there. So that means that the local vortex sheet strength is, in fact, just the velocity just on the outer edge of it. So here you see already we have zero there and there. That's the other zero is at the front. And we have the maximum velocity in the shoulders over here. Now, why do I get excited about this? Because since the vortex sheet strength is only the velocity, and we can calculate it theoretically, but we can also very easily do an experiment and actually measure it, because we can measure the velocity there. So we can compare what we actually see in the real world with our theoretical vortex sheet. And now a nice video from Pascal, he did exactly that. So now this is the first time you see this. This is a view of the whole flow field, and we're kind of coloring in something we call vorticity, which for now you may just assume is similar to that vortex sheet strength. And so that cylinder right now is at rest, and we're now moving it, accelerating it to the left. And there we go, and you now see that on one side we see lots of red, on the other lots of blue, so that's vorticity of opposite sign, or vortex sheet strength of opposite sign. And if we now look at what we're actually getting, then you see the solid line is the potential flow solution you've already seen, and those symbols are actual flow measurements. And once again, we're very early on in that acceleration, and it is right on top of the potential flow. So we shouldn't be too surprised because we've seen that before. And that allows us another way to look at that added mass force, because if a cylinder that has just accelerated has a vortex sheet like that, well, that's very similar to if we had a blue vortex over there and a red one over there, and they're a distance d apart. Since they were created out of nowhere, there must be a force, and that is our added mass force. For the flat plate, it's exactly the same. So here's the flow field. This is the potential flow prediction of the vortex sheet. This is what we're measuring. And if we again look at the numbers, early on, we're right on top of the theory. Of course, there's a bit of smearing. It's quite a hard measurement, but it works very well. So this vortex sheet, which I quite like, is quite useful for us to understand things. And one thing you've seen now is that when we accelerate something rapidly from rest, we're creating, at first, a vortex sheet that is exactly what we would predict from potential flow. And that is also the time when the force we're getting is this added mass force. So I am linking the added mass force to what I call the potential flow vortex sheet, which means whenever the vortex sheet looks like we predicted from our simple potential flow, that's when the force is the added mass force. And in impulsively started flows, that works very well. But only for the first split second. What about a little bit later? Is this all very abstract and it only matters, just at the beginning of this experiment there? Well, let's see what happens later. So here we are. I stopped this before. Now we keep moving this on. And you see that after a while, the actual measured vortex sheet looks nothing like the potential flow. There's clearly a departure here. But then you look at this flow field, and what you see is we're throwing vorticity into the flow field. In fact, we've generated a pair of counter-rotating vortices here. And that is also the time S over D is 1.74, so we're over here where the force is quite different from the added mass force that we would predict. So there clearly must be a connection between the two. Why does this happen? Well, we have flow separation. The flow is leaving the surface, and that requires friction, which we can't really model with potential flow. And it's the same for the flat plate, that here very early on already we have separation at the edge, which is why very early on we already see something different. So that may now ask you, you may now ask yourself the question, well, in that case, is this added mass force, does that only matter once when we accelerate something from rest? And at all the other times when we accelerate something in a flow field that, say, is already very complicated, we don't have it. That's a very good question to ask, because the flow certainly doesn't look like potential flow, so should we still have that added mass force? And there is an experiment that Simon did a long time ago, which I find really exciting, but you need to be a little bit of a fluids nerd maybe to find it exciting. But I'll try and explain. So this is a flat plate, again, but this time we're not accelerating it linearly, we're just rotating it. So we're rapidly accelerating it to rotate, and then we're stopping it rapidly after 180 degrees. We won't get a force, we will get a moment. It's also very pretty. It's super slow motion, so when we first accelerate it, we do get separation in the edges. We create two, and of course, opposing vortices again. You can see that very nicely, and then a few smaller ones. But we always get a mirror image, which is kind of neat. And then we stop, and now we generate two more vortices that are the opposite of the one we generated in the first place. And now we take some proper measurements of this, and again, we cover in the vorticity. So this is what that looks like. And you see very quickly the flow field gets quite messy, quite complicated. And now we stop. And if we look at the potential flow solution, there is one for that. It's a bit harder to get to. The streamlines, as you can see, they look really weird because of the stationary frame of reference. But the vortex sheet on the plate should look like this. We should have a lot of peak vorticity on the edges, and then the opposite vorticity through the middle of the plate. And if we go to our measurement, this is what we see. And if we plot the measurement on top, then we see after the initial start, again, we do get our potential flow. Now that we expect. But what about later? This is what the flow looks like just before we stop. This is what the flow looks like just after we stop. So between those two pictures, we had that sudden deceleration. And at first glance, okay, this is a little bit more noisy, so ignore those blue dots. That's just noise. Sometimes happens. Sometimes you get more noise than in others. So you can ignore that, trust me. The flow looks exactly the same. It looks like nothing has happened in that deceleration. So there might not be any added mass force. But if we take the difference, because we have all these measurements, we can take the difference in velocity between those two. We get this. And if you look at that, that looks like a mirror image of this. And indeed, we exactly recover that potential flow solution, but now the opposite, because we're doing the opposite acceleration. So that added mass, that potential flow vortex sheet is still there. It's just hidden by all the other garbage. So that means there will still be an added mass force when we stop, which is why when I was trying to explain it to you, I can go backwards and forwards. Every time you accelerate, there is an added mass force. So this potential flow vortex sheet, every time you accelerate, no matter how messy the flow is, you will get that in addition to what you already have. It explains the added mass force at any time. Every time you accelerate, you get this. But in a complex flow, it is hidden by other vorticity. And where does that come from? Well, I think you will already guess it, because every time when the flow separates, we shed vorticity through the flow field. Here is a picture of separation of the trailing edge, and you see some stuff's coming off. You've already seen that. Here it's even clearer. The flow separates, and it is shedding all this stuff. This is the vorticity that potential flow doesn't really predict, because it doesn't deal with separation. Does that mean we can't do anything here with potential flow? Well, actually we can. As long as we, if we know what we have shed and where. So for example, imagine that flat plate. Let's say we have just suddenly created this vortex. That vortex has just left the surface. In our potential flow thinking, that needs an equal opposite because of Kelvin, which means that there must be a mirror image on the surface. And in fact, the mirror image will be some, if we're thinking in terms of vortex sheets, it will be some distribution of vortex sheet, which actually we can calculate. If we know where this guy is, then we can calculate this distribution. I won't bore you with how to do that, but that can easily be done. You do need to know where that is and how strong it is. So if we can calculate that, we can then add on top of that the potential flow solution that we had already. And that now allows us to model this flow with a simple tool, this potential flow theory, even though it can't normally do friction. So we're kind of fudging it a little. And that is what the people did 100 years ago when they came up with practical solutions. And that's really what I want to sell today. Now, we need to remind ourselves what assumptions and limitations they made. The solutions I show you today are all to do with wings or airfoils. So we kind of said we're limiting ourselves to vorticity being shed at the trailing edge and no separation here. That's the assumption in the theory, because you need to know where this stuff is going off. What they've also done to make it more tractable is they linearize the problem. That's a mathematical technique where you throw out anything you don't like, basically. That means, technically speaking, you can only really deal with small changes, with small things, with small angles of attack, which sounds very limiting. The advantage is that you can now add solutions on top of each other linearly. So if a change is twice as big, you get twice as much change in the solution. And here's the first of these solutions that I really like by a chap called Wagner, who published this in 1925. So here we really are 100 years old. That's his original figure. It is quite messy. So what he basically computed is a wing that is impulsively, so that is instantaneously at full speed from rest. What is the lift? And the red curve is the one you want to see. That is the lift curve. So what happens is, when you right at the point when you've accelerated, you're already at full speed, you're only getting 50% of the final lift. And then the lift rises very slowly and asymptotically to the final lift. Now you may ask yourself, hey, that's a bit weird. We're already at full speed. Why are we not getting the full lift? Well, remember the starting vortex we've seen earlier. So the vortex sheet can vary in strength. So early on, you just have lots of vorticity right here. A vortex that rotates like this. And remember, the potential flow solution for a vortex says you get a velocity that tails off with 1 over r. Anywhere upstream of the vortex, you now have a downwards velocity. So, and this vortex in the beginning is quite close to that wing. So the wing is suddenly feeling a downwards velocity because of itself. But that means the angle of attack is less than you thought, and you're not creating as much lift as you want. And you need to wait for that vortex to wash all the way back before you finally recover your full lift. So that is what this solution told us. Initially, just half the lift, and then a slow asymptotic rise. The other solution that's very useful for us for our unsteady flow problems is that of a wing suddenly meeting an updraft. This is so this gust goes on forever. So the wing moves through still air and then comes into a flow field where suddenly there's a strong updraft or downdraft. And a chap called Küstner developed this. He published it in 1936, so I'm stretching my 100 years a little bit. But this is what his lift prediction looks like, and very similar to Wagner. Again, a slow, gentle rise. So, what have we done? All of this is old stuff. And now I come to my current PhD student, Paras, and Ignacio, who's just left a while back. What they have done is they've thrown this all together. So we start off with our added mass force. So every time, if we want to model a wing, like a bird flapping, every time it accelerates, we throw in an added mass force because we know it should be there. Whenever there is a streamwise acceleration, when the wing suddenly moves forward or backwards, we throw in a Wagner term, which you've just seen. Whenever there is an outside gust, any velocity outside, we throw in a Küstner term. And we add all that mathematically. Now, there is just one problem, that Wagner and Küstner assumed perfect step changes. And the real world, of course, isn't like that. But it turns out there is a relatively easy way to deal with it. I can sound very fancy and say it's a Duhamel integral, but it's actually very easy because what you do is this is what, for example, Wagner has assumed, that an airfoil is at rest and then suddenly at full speed, and that's what the lift curve looks like. In reality, we might have an airfoil that accelerates more gently. So how do we deal with that? Well, we just break it into lots and lots of little steps, little Wagner experiments, and because it's linearized, we're allowed to add them all up on top of each other, and so we get something like this. And that gives us a solution for any sudden change for any change in velocity, not even an impulsive one. And if you do that, you get something like this. I don't expect you to understand it. I don't even understand it. That's what I have my students for, so thank you, Paras. But there's a W which says Wagner, there's a K for Küstner there, so you can see it's all in there. And does this work? Well, let's try it. So the first test we did was the gust encounter. This is actually quite a tough experiment to pull off. That's why we went for it first, because nobody had done that before. And for that, we're doing the experiments in water in the tow tank. That was designed by John Harvey, who's also here today. So when he wasn't busy designing wind tunnels for Formula One teams, he designed that tow tank for us. And we're doing it in water because water and air behave the same. They're both incompressible. We're treating air as incompressible. But the time scale varies. In water, it's like you can do everything in slow motion. And you get nice big forces, which are easy to measure. And so we're having a wing on a carriage. So we're moving that through the tow tank. And then to create a gust, Simon, who's not here today, built effectively like a wind tunnel that goes transverse through this thing. It blows it blows water across, and then we just move that wing through that gust. And here's what this looks like in the lab. So you can see there's some proper hardware. So this is quite a long way away from doing things with pen and paper. This is quite exciting, and you can get wet if you get it wrong. And here is a super slow motion, so you can't see at the moment where the gust is. It's moving in this area. Here's the wing, and I just love this video. I think it's very pretty. And it's all self-explanatory. So at first, nothing happens, and now we enter the gust, and it immediately separates at the leading edge, and there's also, you see, there's your shear layer coming off at the back. When you look at that, that does not look like potential flow. So we're a long way away from potential flow. Here's now the proper quantitative experiment, and on the right, you will see the force response. So what happens? We enter the gust, and immediately there's a big force experienced by the wing. And then obviously when we leave the gust, it all calms down a bit. If you know anything about aerodynamics or aviation, a lift coefficient of 6 is pretty massive. That is enormous. That can probably rip your wing off. So this is very large indeed. So these are very, very strong gusts. So we have this theory that is built on small changes and things being very subtle. How does it do? Well, here it is. So the theory is that dashed line. And I'm giving you two experiments with two so-called gust ratios. The gust ratio is how strong is the gust relative to the flight speed. And why am I showing you only one prediction? Because the theory is linear. That means twice the gust, twice the force. So what we've done is we've divided the lift coefficient by the gust ratio, and then in theory, everything should be on top of each other. Of course it isn't. This is the real world. But first of all, let's look at the gust ratio of a quarter, which is still a whopping big gust. I trust you don't want to fly through that. And that matches the prediction really remarkably well. And the gust ratio of 1, yeah, it doesn't do quite so well, especially once we leave the gust, but it's actually not bad, considering that the flow separates at the leading edge, and of course our theory assumes it doesn't, that the effective angle of attack at a gust ratio of 1 is 45 degrees. That's not a small angle. So it really should be nothing like this good, and yet it is, which is great. Now, in reality, your gusts aren't just that one type. In reality, you might be flying through atmospheric turbulence where you have swirly things, and this is where Paras comes in, our current PhD student. He is looking at a so-called vortex gust encounter. So what happens if a wing meets a vortex? How do we do that? Well, remember, where we can pitch a wing and create a starting vortex, and that was Paras's experiment. So now we just put a second wing that follows it. And this is relatively hot off the press. So on the left, you will see the flow field. On the right, the dashed line is the predicted force with that equation I've shown you. And in black, you will see in real time the force. And so here we're creating the wing, the vortex, sorry. So this is just creating the vortex. There's the vortex, there it's meeting the wing. And, well, obviously he gave me his most impressive result. But it is still, given the simplicity of the theory, it's really remarkable how well that works. So we seem to have found that these 100-year-old theories can actually still give surprisingly accurate predictions. So can we do something with that? Well, yes, we can. I'll just give you a quick example. What we can do is, here's the equation. It has the lift force over here. What we can now do is we can set that to constant. We put the gust in here and say, how do we need to move the wing in order to get a constant force? So the idea is that we invert that and then pitch the wing accordingly and see if we can mitigate the gust force. So let's try that. Here's the same gust you've seen before. Here's the force you've seen before. And now, however, we're using the pitch profile we've calculated that it should do in order to not get a force. Of course, it's not perfect. It's a linear theory. It's simplified. But if you look at this is something like a 95% reduction in force. It just really works remarkably well. And now you say, well, you're coming in at zero angle of attack with no lift. What use is that? Well, we've also done it coming in at an angle of attack, which with a flat plate airfoil is really not such a clever thing to do because it doesn't work very well. So we're already starting being outside of the range of validity of potential flow. And yet, when we look at all the results, here are all the mitigated results. They're much better than the ones before. The one that doesn't work so well is here, where we're coming in at a 20-degree angle of attack. We're really stretching our small angle assumption. But again, on the whole, we're getting remarkable mitigations. Some other cynic might say, well, what if we have a downwards gust? Because these can be even more dangerous when you suddenly lose all lift. And we can do that too. Now you have to pitch up to create more lift to compensate for that strong downwards force. And here you see there is the downwards force if you don't do anything. Here it is with doing something. The 20 degrees is again the one that doesn't work so well, but the 10 degrees works super well. And this is far better than any other gust mitigation that people have tried. We've now moved on, and we're doing it with a flap rather than pitching the whole wing. This was just to test the concept. Now I'm coming to the end of my talk. I just want to talk about one other use and show you a picture which is very, very recent. This was taken about 9 days ago. This is the America's Cup final race between Ineos Britannia, which is the boat in the back, and Team New Zealand, which is the boat at the front. So why am I showing you this? Because I've been talking about my PhD students, and Paris is still here, but the other three went off to work for those two teams. And they told me, if you don't know anything about America's Cup, I encourage you, just Google it, just look at some videos. It is remarkable. These are 20-meter long yachts that are suspended on a hydrofoil that is about this long with this much course, and they're just balancing on that one wing under the water, and they do the most crazy things. It really is exciting. Anyway, the point is, why did they hire these students? It turns out that unsteady aerodynamics actually matters for this. And in fact, I know for a fact that the Wagner term that I just talked about, and plus some of the other things, have been put into the modeling software that the teams use to design their boats. And you might ask yourself why that is. Well, here's a picture also from the race. When you see the videos in real, these maneuvers that they pull are absolutely remarkable. They pull pretty high G-forces when they go around a corner. And so actually what you see is that within just 1 or 2 chord lengths of, if you say the chord length is the length of the boat, they change direction very radically. So these unsteady terms do actually matter, and they make a difference, so I've been told. So 100-year-old theory, still in use today. That old equation was put into the model. So with that, I'm sort of coming to the end. I want to say that unsteady flows can produce very large forces. They also occur a lot in daily life. That these old theories still have their value. Yes, we can simulate a lot of things with fancy computer programs, but these old analytical things are really useful because they give us an understanding, even in a complex viscous flow. Even when they shouldn't work, they do work. So there is really something fundamentally important in there. And also, these equations can be solved really, really quickly. So for example, on the wing, you just need one velocity sensor, maybe a meter upstream that gives you enough time to solve that equation and decide what the flap on the back of the wing needs to do. And the better understanding, of course, helps us to design better. And just before I finish, I want to again thank the 3 students who've left. Paras, who's still here, John Harvey, who designed the tow tank, Will Graham, who's not here, who helped with a lot of the math. And sorry, Pascal, I have to show you this because I'm just so proud of them. So this is Simon and Ignacio last Saturday. This is the America's Cup. And so now, I think it was totally obvious from the start who was going to win because Team New Zealand had 2 Cambridge students and Ineos Britannia only had 1. And as good as Pascal is, he couldn't compete with 2. So thank you very much for listening.